The emergence of convolution is our next topic. And we're going to talk about what that means. But basically, today, we'll be talking about feature extraction. And this is a really important part of computer vision. And we'll be talking about some methods for feature extraction. Some older methods are called SIFT and HOG. And those are what you might call conventional feature extraction techniques. And then we'll talk about convolution, which is many times and in many ways a better technique than SIFT and HOG. So these are the three things we'll be talking about today. Let's start by talking about feature extraction in general. Well, look at the two images here at the bottom of this slide. On the left, you have an original photograph. And you can see, just like we've talked about before, image data is stored in a rectangular array of pixels. And so in one sense, if you want to describe this image, you have to describe every pixel. This pixel's a little bit gray, this pixel's darker, this pixel's lighter. Now we have an orange pixel. And that can be a very complex description because you may have hundreds or many thousands of pixels. On the right, you see the results of one process for feature extraction. And the idea is that we don't really want to describe every single pixel in this entire image. We want to describe something that's simpler and more generalizable. And so, for example, you might say, well, instead of telling you about every pixel of this duck, I just want to tell you in general, it has a head that's kind of curved. It has a bill or a mouth that's kind of straight like that. It has a tail, it has a wing that has this kind of straight shape in this sort of direction. And you can see that that's sort of a simpler description than describing every single pixel. If we just describe the contours or the outline of the duck, it becomes a little bit simpler to talk about the duck. It also becomes simpler to compare. If I have two different images, one image of a duck and another image of a different duck, well, if we look at them pixel by pixel, we might think that they're totally different images. We might say, oh, look, this has a slightly darker pixel here and this has a slightly lighter pixel. We might get caught up in these differences. But if we just look at the contours and the outlines and say, oh, look, this has a curved head, this one also has a curved head, so these maybe are images of the same thing. So by doing feature extraction, we just look at the simple, most important aspects of an image, and it makes it much easier to compare different kinds of images together. It also makes it easier for us to do machine learning with images. So instead of doing machine learning with every single pixel of an image and all the complexity there, you can do machine learning with just some general, very simple features. Just say, okay, a general curve here, a general line here, and you haven't lost much information about the duck, but you've made it much simpler for all the techniques you want to use. That's why we do feature extraction. So I think the idea of feature extraction is pretty simple. We take a complex image and we want to describe it in simple ways. However, how do we do that? If you had to write a computer program that does feature extraction, how would you do it, or how would you describe it mathematically? That's a harder question to answer. So let's talk about how we can answer that. Well, first, let's look at this slide and make sure you feel comfortable with all these aspects of feature extraction and what it means. Just like I said, we want just the essential information. And if we get just the essential information, like a straight wing here, a curved head here, things like the outline of an image, that can help us improve model performance for machine learning. It can help us convert between images. At the bottom of this slide, you can see three different feature extraction methods that are being described: HOG, SIFT, and convolution. And we will talk about each of these. But each of them are, they're based on mathematical ideas, but they're things we can write code for. And they each are going to try to take complex images and just find the simple outlines or the simple features of these images for comparison and to improve model performance. So let's talk about some of the older or more conventional feature extraction techniques. Well, two of them are being described here. One of them is called HOG, and the other one is called SIFT. Well, let's talk about HOG first. HOG is short for histogram of oriented gradients. Well, you may already understand what a gradient is. if one side of your image is white and one side of your image is black, and then maybe there's this transition between white to black where it gets darker, then you could say that that image is sort of a gradient. And instead of measuring every single pixel of that image, you could just measure a vector that says, okay, there's this gradient where it gets darker in this direction. But you could have a different gradient where it's light at the bottom and dark at the top. And then you could sort of measure that in a different way. You could say, I don't want to measure every pixel. I just want to say it's getting from lighter to darker in this direction. Or you could imagine a gradient going in any different direction. And whatever direction your gradient goes in, you could just create a vector that tells you which direction that gradient is going in. Well, a picture of something like a duck, it's more than just a gradient. It has a lot of different little features. So what HOG does, HOG, it will split an image of a duck into many little pieces. And for every little piece, it will say, okay, for this little piece of the duck, what's the direction of the gradient? Is this like, the top of the duck, or the top of the duck's head is dark and the bottom of the duck's head is light? In that case, instead of storing every pixel about the duck's head, let's just store a gradient that says, okay, it's getting darker or lighter in this direction. So HOG is just a bunch of different vectors that show the gradient of where things are getting lighter or darker in the image. And we'll be looking at examples of that soon. SIFT is a more complex method. It does also rely on gradients, but in addition to relying on gradients, it's relying on points of interest. So what it does is it identifies, if you have a picture of a car and then like a clear blue sky, it kind of says like, well, the blue sky, every pixel is the same in the blue sky. So it's not too interesting to just look at this area where everything's the same. But on the car, we have these sharp contrasts, and the dark part of the car and the light part of a car. And where you have sharp contrast, that tends to be like a point of interest. It tends to be more interesting to look at a part of an image that has that contrast in it. So SIFT, it identifies the points of interest, the high contrast points, and then it does some other calculations, things like gradients related to each of those points of interest. So both of these are ways to sort of simplify an image and sort of boil it down to just features instead of all these different pixels. So you can see this comparison here. HOG is interested in structure and shape. SIFT is, it's looking at these coordinates of these most interesting parts of the image. And SIFT is really flexible in the sense that even if you rotate your image or if you make your image bigger, SIFT is going to give you the same results. With HOG, that's not true. If you imagine like a little piece of the duck's head has some gradient, but if you make the duck much, much bigger, then a little piece of the duck's head is just going to be, the same color everywhere, because now the duck's head is huge. So when you take little pieces, you don't have gradients anymore. So when you scale and rotate, HOG can be affected, but SIFT won't be affected. And potentially that can be a good thing, because if you have a picture of a duck that looks like this, and then you have a rotated picture of a duck, you want to know that these are actually the same thing. They're both representing a duck. And so the flexibility that SIFT has to recognize rotated and scaled images is an advantage that it has. So here I talked about the points of interest, or the key points. And HOG is, identifying magnitude and direction of gradients. And we'll talk about that more soon. So these are two conventional feature extraction techniques. Let's keep looking. These are some examples of HOG and SIFT results. And so just like I was saying, if you look at this image of a duck, you can say, okay, the top of his head is kind of dark, but then this part of his head is kind of light. So when you look at this part of the HOG results, you can see these gradients are pointing in the direction of where the head is getting darker and lighter. But points where the image is sort of homogeneous and there's not much of a gradient, like this water where it's roughly homogeneous, you don't see many gradients there. The gradients are showing the direction of getting lighter or darker. And just by knowing the directions where things get lighter or darker, even though that's really simple information, it can already sort of help you understand where the edges are and what you're sort of looking at. So this HOG result, you can sort of tell it's a duck, even though it's only storing a few vectors instead of thousands of pixels. So you can see it's simplified the image. SIFT, what's being identified here by SIFT is what are called the key points, or points of interest. And like I said, these are the points of high contrast And SIFT sort of believes that your eye is naturally going to be drawn to these points of high contrast. And SIFT will be good at identifying these points of contrast. No matter how you rotate or scale the image, it'll give you the same results. And after it identifies those key points, it records other things about them, things like gradients and other things as well. But it's mostly focused on these key points and points of interest. So these are a couple of feature extraction techniques. Well, why are these not so perfect? Well, let's talk about it. We talked about how SIFT is unaffected by size and orientation. So HOG, histogram of oriented gradients, when you make your image bigger or smaller, or when you rotate your image, you could get totally different results. And that can be a problem because we want to compare images of different sizes, or we want to compare rotated images without getting distracted. And so HOG might not be the best method for that. SIFT can compare images. It can understand that two images are the same, even if one of them has been rotated and the other one has not. And so, that's why SIFT potentially can have better accuracy than HOG. But both SIFT and HOG have some disadvantages, and they're described here. Well, they're pretty slow. You have to calculate gradients for every single little part of an image. That can take a lot of computation power. They're a little bit complex mathematically, and HOG has some problems where if there's blurring or if there's lighting changes, HOG doesn't work so well. So these are methods for feature extraction. They're conventional, they're a little bit older, but they're not so perfect. So that's why we want to introduce a better feature extraction technique to you. And that's why we're going to talk about convolution next. Convolution is a better feature extraction method. So convolution is really, it's a linear algebra operation, or you might call it a matrix multiplication operation. So convolution, to do convolution, you represent an image as a matrix, and then you create another matrix called the convolution matrix. And really all you do is kind of multiply these matrices together in some sort of way. So you multiply an image matrix by a convolution matrix, and you get some result which shows your features. And we're going to show you some examples of that. And that's what's being described here on the slide. Filters called convolution layers. When it says filters, it's talking about those convolution matrices I talked about. And layers, like sometimes you do multiple convolution matrices, so you multiply by this one and then you multiply by this one. That's why we talk about these layers of convolution filters. But really it's all just a type of matrix multiplication. And so here's an example. We have this image of a brick wall. So you could imagine there's so many pixels here, there's so much information in every pixel. But we want to boil this down to just a really simple description in terms of some simpler features. And that's what we're going to try to do. And so this first image you see here is the result of vertical edge detection. So it turns out there's a certain type of convolution matrix you can use. And if you multiply that convolution matrix by this image, you get this result. This is also an image, but it's a multiplication of the original image by a convolution matrix. And you can see that it's pretty much just showing where there are vertical edges on the brick wall. It's not telling us much about horizontal edges, but it's saying, at these certain places there are vertical edges. If you multiply a different convolution matrix by the original image, you get kind of detection of where the horizontal edges are, but not really information about where the vertical edges are. And so you can see that this is really simple. It's just multiplication of some little matrices by a big image matrix. But you can see that we're getting what we call low-level features. We're not getting like the full outline of a duck's head and every little piece of their feathers and everything. We're just getting something really simple. What are the vertical images? What are the vertical edges? What are the horizontal edges? It's a very simple result that we get, or a low-level result. Well, convolution matrices are very powerful. They can you can find one convolution matrix that will find the vertical edges for you. A different convolution matrix gets the horizontal edges. But there are certain convolution matrices you can use to blur an image, or to reverse a blur, to sharpen an image, or to highlight or focus on certain parts of an image. Just by specifying a different matrix, when you multiply that matrix by the original image, you get these certain different results. And so these are the examples: vertical and horizontal edge detection. But there are many other things, many other low-level features that a convolution matrix can identify just by doing that special kind of multiplication. Well, why is convolution better than these other methods? Well, like I mentioned, there are many different types of convolution matrices you can use. You can use a vertical edge detector, a horizontal edge detector, but there are all sorts of other convolution matrices you can use, and they can detect many, many different kinds of features. That's why it's saying this, that they're highly trainable and adaptable. Hog and Sift, they'll just give you one output, the same output every time. But with convolution, you just change little parts of your convolution matrix and you get different results and detect different features. So depending on what task you're interested in, you can choose a convolution matrix that's perfect for the task that you like. And then, I mentioned low-level features. If you remember the Sift and Hog output, there were so many gradients and so many key points, and it was sort of, trying to understand our image sort of at a high level. And low level means very simple things like just vertical and horizontal edges, sort of learned one at a time. And you don't have to do hand-coded feature engineering, which means you don't have to like crop out a certain part of the image to say, here's the head of the duck, here's the tail of the duck. Convolution is going to sort of identify features without requiring that kind of hand coding for you. Well, the interesting thing is that if you do enough convolution, not only can you get low-level features, but you can get high-level features as well. So if we do one convolution to identify vertical edges and another convolution to identify horizontal edges, then we can combine those results and find where all the T's are, find where a vertical edge meets a horizontal edge, or find where all the X's are. And then if you keep doing convolution with more and more filters and more layers, you can find very complex shapes. You can find where a T meets an X, or where there's some kind of special curve. And that's like sort of building up high-level features and high-level shapes from these lower-level, simpler shapes that we've identified. So by doing multiple convolution matrices or multiple filters, we're able to build from low-level to high-level features. And so if you're recognizing like a human face, there are some low-level features on the human face, like maybe your eyebrows are mostly like a horizontal edge, and maybe your nose is mostly like a vertical edge. But by doing convolution a lot of times, you can get a concise description of an image that describes those vertical and horizontal edges, but also describes, okay, the nose is this far from the eyebrows, and the forehead is this big, and the mouth is this big. And it can understand both low-level and high-level features of a human face, and it can help you recognize a person's face, with code instead of needing to look at that person. So these are some, advantages or good things about convolution. And, in practice, once you use convolution, your machine learning models can run faster and often get better accuracy. And this is an example going back to 2012. There was this invention called AlexNet. Well, AlexNet was a neural network, but it was one that relied on convolution to do feature extraction. So you start with an image, you do this convolution for feature extraction. The results of that convolution are the inputs in your neural network. So we call it a convolutional neural network. And when they had that competition in 2012, this convolutional neural network did really, really well and won by a comfortable margin. And so convolution, is something that people have studied for a long time and they already knew about it. But it's sort of just by combining these things, by combining convolutions and the power of neural networks, that we got CNNs and we got this great performance. And and in general, we say that we have both superior and more generalizable results from convolution. So instead of just saying, well, I have this feature extractor, but it only works on ducks, convolution is something that can work on, any type of image that you have. So it's kind of more generalizable without requiring as much hand coding. And so these are some good things that have come in the world of machine learning from convolution as a feature extractor. So that's all we're going to talk about for now. Thanks for watching.